Okay. Let me give you a definition here. The last time we talked about what it meant for automorphisms to be linearly independent, and found that you have a collection of distinct automorphisms, they form a linearly independent set. Definition. 875, we say F is a spectrum. Okay, here, of course, every here feels. If F is Galois over Galois group of F. So I think that the terminology is, I think, fairly straightforward. If you ever hear the term cyclic extension, it just means it's Galois, cyclic Galois group, Billian extension, same for Billian. These are important classes of rings, and in fact, there's lots of good results in number theory that come in these particular cases. And in fact, we will see a couple of results here in the next theorem that depend on the cyclic theorem. 876. In this situation, we have F is cyclic. Degree n. And of course, what this means is that the mention of the field extension F over K is n, and it means that the degree of Galois, or the form of Galois F over K is n, and it's of course a cyclic group order n. And we'll let sigma be a generator of the Galois group. An element of F. Number one, the trace zero. So under what conditions is the trace of this element F, U and F zero, if and only if U is the form B minus sigma B for some B and F. And number two, this is popularly called Hilbert's theorem 90. And it's the same thing, only multiplicative. That is to say, the norm one, if and only if you get an analogous multiplicative result. That is, U equals B times sigma B inverse for some B. So in other words, elements of trace U, elements U that have trace zero take on a very specific form. It's B minus one of the conjugates of B, where in fact none is any conjugate can generate a conjugate. And if the norm is one, it's specific as well. verify this that way is the easy way, because notice if I have, let me talk through the trace, and it's the same thing. Notice that this is Galois, right? So what is the trace of Q? It's the sum of the conjugates, right? So imagine just conjugating all this and adding up the columns. U, sigma squared U, all the way down here. You add up that column. That sum is going to be trace of U. And then when you sum this up, it's trace of V, right? So what we have is trace of U, trace of V. And what happens here when you sum this up? Well, what you have now is, so maybe I'm blind. Right? So when you add the last one, you get sigma V, sigma squared V, sigma n minus 1, sigma n. Right. And then when you multiply that by sigma to the n minus 1, you get V. And when you add this up, you get the trace of V as well. Right? Because think about what we've done here. We apply first the identity, then sigma all the way up to sigma to the n minus 1, which gives you V. So now you're just adding up the same thing you did the other column in the opposite order, and it sums to not the opposite order, a different. It's very similar to this. The interesting part, of course, for this theorem is if you have just any old garbage element of trace 0, then it actually turns out to be this form. So let's take that one apart first. Let's suppose the trace U is 0. And I will suppress all the superscripts here, just to make this quick. We choose an element such as the trace of W is 1. Let me justify why you do that. Such that sum is not 0. Because all those powers, well, of course, Z, that's the identity automorphism. They're way over on the far left. These are all distinct automorphisms, so they're linearly independent. So I should be able to find some Z such that, well, when you plug in Z this, you get something that's non-zero. And what I now do is I now let W let W equal 0 trace. Notice this, in fact, since this is not 0, notice this is the trace of Z right here. It's not 0. 0 trace Z. It's easy to check that 0 trace Z actually has trace 1. Because when you go through the automorphisms and add them up, you basically get trace Z on the top. The automorphisms always trace Z alone. So you get trace Z and trace Z. Okay, so first hump we get over here and say, I want this W in here, such that the trace of W is 1. Now, what I'm going to do is I'm going to let V be, and I want this computation for, and I think I got it right. Every time I have to talk about Hilbert serve, I need to check myself on this. But V is W actually, U plus sigma U, sigma W, and then 2 plus sigma U plus sigma squared U of sigma squared W. And this pattern continues. When we put in the last term, sigma U, sigma squared U, sigma n minus 2 U, sigma n minus 2. Right. So I'm going to take the B to be this element, right? Hopefully you see the pattern, right? You're increasing W, sigma squared W, all the way to sigma n minus 2 W. And you're growing this here, U, and now the sum of first two conjugates or two conjugates, first n minus 1. Now, what I want to do is I'm going to hit this with actually, let's go ahead and do this. What's sigma of the let's do the panes of this. This is sigma U, sigma W. And notice that comes up here. Right? This is sigma U, sigma squared U, and sigma squared W. Right? Which is kind of most of this piece right here. Sigma U, sigma squared U, sigma cubed U, sigma cubed W. So it's basically it's going through. It's just jacking everything up a little bit. Sigma U, sigma squared U, sigma n minus 1 even sigma n minus 1. Now, there's an incredibly important observation that we need to make here. And this might be a really good for us. Anybody tell me what that chunk is right there? Oh, that's a key observation. That's exactly right. It's the trace, but it's missing something. Let me write down the trace. By the way, what are we assuming about the trace view? It's 0. Right? So what is this? That's minus. I'm going to make that perfect. So let's analyze this. Let's look at V minus sigma V. Well, let me take this apart piece by piece. There we go. Notice sigma U, sigma W, sigma u, sigma w, that cancels. When I subtract, and all that I'm left with is u sigma w, right? So now I've got everything up to here accounted for through here. Next step, I'm going to take this garbage and subtract off this. Notice we've got a match. This. So now you're dead up to here and here. And all that's left over is u sigma squared w. Everybody okay? And the last bit u sigma n minus 2 w. And notice this thing right here is the only thing left over, but it doesn't have something up there to cancel. But fortunately for us, this is minus u sigma n minus 1. So what we have is v minus sigma v is equal to u times trace w. If I jerk that u out, then I'm left with trace w. And trace w is 1. And there we go. Okay. Good questions. I'll do the other direction on Hilbert's theorem 90 as well. It's similar. In fact, it's like it's a little bit easier. I think. Well, so for the other direction, we have norm of u equals 1. We find y and f such that it's down v qy plus u sigma y u squared and then the last term is 1. And this is not so similar to what we did with the setup of the additive version of trace. Convince yourself that you can find something of this form by independence that's not 0.
Special with the normal y, like we did the trace of w, and we wanted the trace of w.
Yes, I just want this to be honest. Notice that this, oops, Notice that this is the norm of U. So this last bit is just, this is just gone. So it's just assumed to be in minus 1 y. So let's look at the inverse. Let's look at sigma B. This is sigma U, sigma Y, plus sigma U, sigma squared U, sigma squared Y, plus sigma U, sigma squared U, sigma Q. And let's see, I guess this would be sigma U, sigma squared U. One sigma n minus 1 y plus sigma n y. So I dutifully march up here, applying the sigmas here. The last term I will get, of course, is sigma to the ny. In the previous term, I guess you terminate at the sigma to the n minus 1 y like that. And notice that this is and notice notice that sigma ny is y, because sigma to the n is the identity. Now, notice that U sigma B, this means tagging a U on everything, and I'll take the liberty of putting this y first. Basically adding a U to everything on the left. It's U, sigma U, sigma squared U, sigma n minus 1, U, sigma n minus 5. Notice this is the recovered B. All right. So let's get matched. And so solving this for U, I get U is equal to B, sigma B. Any questions on that? That's really a neat little theorem, and it does depend very heavily on the fact that Galois is cyclic. Let me throw out there kind of a neat application of Hilbert's theorem 90 that will recover some of you. How many of you have ever seen how many of you have ever seen so you all know what the Pythagorean triples are, right? Like 3 squared plus 4 squared is 5 squared and so forth. And now you can always re-rationalize this. If you take any Pythagorean triple, you can restate that as 3/5 squared equals 4/5 squared equals 1. We can do like 5 13 squared plus 12 13 squared equals 1. How many of you have seen parameterization of all Pythagorean triples? Count that? Well, actually, depending on number theory, you never can tell what somebody's seen from number theory class because there's so much stuff you can do in number theory class. So who knows what was done? But here's an example. We'll kind of do a neat little application of Hilbert's theorem 90. Notice that Q inside QI is cyclic. Of course, it's cyclic more too. And if sigma is complex conjugation, then Galois group of QI with Q is generated by sigma. So our role of sigma here is played by complex conjugation. Now suppose that you have A, B rational numbers, so it's norm A plus BI is 1. So A plus BI is an element of QI. Its norm is 1, and essentially that means it kind of sits on the circle. This is equivalent to stating that A and B are rational numbers. Such that A and B were their solution to but because the norm of A plus BI is basically equals B squared. So Hilbert's theorem 90 says there exists C equals X plus y such that X plus BI is C over norms. Or I'm sorry, sigmas. That is the complex conjugate. Now, we can assume at this point in our simulation, because if they're not, all I have to do is collect the denominators and just rationalize it, right? So if I've got if D is the denominator for X and E is the denominator for Y, it's what we'll talk about. And just rewrite this. Now you've got the decimal integers. So now what we do is rationalize this. And when we get to the top, we get x squared minus y squared plus yeah, did that right. Now equating real and imaginary parts, what we get is a is equal to x squared minus y squared over x squared plus y squared. And b is equal to 2xy. And this rather famously parameterizes the Pythagorean triples. You can easily check, well, easily progress to it's different mass, check the base square. And actually, what we see on money basically says this is everything, right? So, you know, if you want your 3, 4, 5s, comes out with rational numbers, start rationalizing, right? Any Pythagorean triple that you want. Okay, any questions on that? Okay, so let me talk about something that you all went over in the last homework, maybe stumbled across some form or other. And we've actually talked about this on certain specific basis. Definition. Say this guy is a primitive infinite unit. Primitive infinite unity if what it means to be primitive is the nth power of this thing is 1, and no smaller power that's greater than 0 works. So, for example, over has noticed that if we're talking about complex numbers, it's clear that this e to the 2 pi I in power is equal to 1, and no small power, no smaller positive power would work. Note only contains plus or minus 1 for primitive or unity. Same is true for R. The real numbers only contain the two roots of unity, right? Yeah, you've all, I know I talked about some of you, but on the complex plane, the primitive roots of unity are the form equal to pi over n. So they sit on the unit circle, right? The only intersection of the unit circle with the real numbers are right there. So that's it, right? Even the reals, as big and fat as it is, only has two primitive roots of unity. Complex numbers has any nth roots of unity. Pick your n, it's got the 8, 6, 7, 5, 3, or 9 of unity. And it's really interesting, isn't it? Because all you need is the square root of -1, and so the reals has only two primitive roots of unity. All you need is the I in there, and you get them all, right? Which is it's really kind of bananas, right? CI things, fourth roots, primitive. Primitive fourth roots community of I negative I. Okay, so remember this one. Repeat this one. The primitive third root of unity. Which roots of unity do you think this contains? You joined. I meant to. I'm sorry, my bad. Got me in a number for you. Save mine here. Fuel weight contains the primitive. That was a little tricky, right? Because 3 is odd. So negative that thing should be actually 6 3. And actually there's items of number theoretic importance to both of these fields because of the fact that let's see. Oh, you're so close. There you go. Right. Because the unit group of this is actually cyclic, right? And it's cyclic over p-1. It's just that generator, the p-1 power is 1 and no smaller. You can generalize this to any finite field. See how it changes that formula. And of course, if ZP contains a primitive p-1 root of unity, it will contain a primitive k root of unity for every k that divides p-1 by taking the appropriate power. Okay. So, proposition. Previous field that contains a primitive nth root unit. number one, if D divides N, then then if you take this to the N over D power is permanent. D. And here's something that's nice. Think about. Got a lot of groups. Splitting fields. If D divides N and U is a root of X D minus A. So A is K. Then X D minus A. D continues. A. Splitting A of U is the splitting field. X D minus A. Okay. Then you okay. Galois and Galois group is cyclic order. Okay, let's sketch this out. I will go through a lot of, number one is not very difficult. If D divides N, then this is a primitive D through unity. Notice that A to the D is the N over D, the power, which is 20, N, which is 1. So it's a D through. Y is a primitive. That's not one as N L over D plus N. Okay, how about the other statement here? D divides N, and U is a root of X to D minus A. Okay. Well, notice that the second statement, primitive. N through 1. You know, and hence, eta D through 1. For roots, so if you here. Yeah, Jim was a little bit sloppy with this in the following sense. Here, we're assuming that I should assume this. This is good. This is near this. Because if it's not, then I sort of go with this last conclusion. Because if it's not, if it's got a root downstairs, right, I'm going to assume that's irreducible. Because if, for example, A is already a deep power of something downstairs, then what will happen is, I think everything in there will be true. So the Galois just be true. Then X to B, I'm saying, are 2 AD X squared. It's easy to check that all of these are roots because the deep power of U is A, and the deep power of any of the primitive deep roots of unity are A. These are all distinct. And so it's a splitting field. So since I've got distinct roots and it's a splitting field, it's Galois. The last thing is, how do I know that the Galois group is in fact cyclic? Well, there is a homomorphism that takes U, say, to A to U, right? And once you go there, all you have to do is go through the compositions to show where everything else goes. And you can show that any power that once I know where U goes, if I select U goes to some, well, if U goes to itself, then that fixes the automorphism. And the reason is because eta is in the downstairs field. Right? So any automorphism, right? So there's nothing that just creates eta by itself because it's in the downstairs field. Once U goes to one of these powers, that determines where every one of these goes. Right? And you can show that actually you get one of them generates all the rest of it. Okay. Any questions? I think this is probably a good place to quit. We should finish this up next time and then get on to a little bit of Dedekind domains, a little bit of maybe beginning towards beginning out. Questions? Here, there, anywhere out there? Well, don't forget, folks, I've got that calculus challenge meeting today, but I should be, if you're in a spot, I should be back to my office by noon. So, I'll see you.